task. This is some joint work which I present today with Virginia Tech and the Queensland University from Australia. And we're basically also combining satellite information with social media. And you might first think of why do we actually need satellite data? And I would motivate this with the UN Sustainable Development Goals. And if you see this, you see that many goals of these actually have this need to quantify things, what's going on in our world. And some part of them, for example, like wildlife monitoring, also disasters. And this is something that we picked up here in this task to focus on. And here are the current disasters which you see from the Organization of Humanitarian Chair for Humanitarian Affairs. And what you actually see in here is that most of these events are actually caused by floodings. Also the hurricanes right now, which you heard from the US. So this really shows that it's a very important problem. And also in the news, you just get these news every day about floodings in different areas. Here, for example, how important it is also to incorporate the satellite information into this. And this is something that we interest in our task. However, if you just look at satellite information itself, is it just enough to have and analyze these images here? It's actually not, because quite often you just have clouds in between, so you don't see the whole extent of the image. Sometimes it takes time for the satellite to revisit it or to receive the data. So we're dealing here with very sparse data. And one way to circumvent this is to use other streams, for example, social media. Like Tom already said, especially for floodings, there's a lot of social reflection also in these streams, which we can basically use for this. So this is the basic idea, that we can combine it and use it then later on in a predictive manner to augment the whole event. So as an overview, we have two tasks in our multimedia satellite task. The first one is focusing on social media, and the second on satellite image processing. For the retrieval task, you see here some tweets basically from Twitter about the recent Houston floodings. And what you see, actually, all of them talk about the same event, about floodings. However, not all of them are really relevant for rescuers. For example, the lower parts here, they don't really provide direct evidence of this. So we want to really analyze the text and visual content in order to filter this information out. And in the second task, it basically addresses the problem of having some satellite information and extracting flooded areas from it by using basically a segmentation problem. For our task, we have basically 5 runs for each subtask, and for the first task, we considered on different modalities, so on visual only, on metadata, and fusion of both. And for the second task, we had also 3 required runs about just using this provided satellite information, and in the last 2 also to incorporate other data, for example, depth information, elevation map, topological maps, or even other satellites. So it was very open also. And we use here standard evaluation matrix, like for the retrieval task, average precision at different cutoffs, and for the segmentation, the standard intersection over union. In total, we have a dataset for this for about 6,000 images taken from the IFCC. These images come along with pre-computed features and metadata containing text, containing location information, and 2 labels about showing evidence of a flooding or no evidence of flooding. And for the second dataset, we basically got high-resolution images from Planet Labs. That's a startup from San Francisco, which has these microsatellites, and they provide a resolution of 3 meters. So you can really see the flood extent quite well here in these images. And we provide also a dataset for this, along with segmentation mask and small patches of 300 pixel size. For the ground truth generation, for the first task, we set up a crowdsourcing experiment. So we asked annotators basically to evaluate how strongly a given image shows direct evidence of a flooding, rating from 0 for non-flooding to 5 to strong evidence of a flooding. And we combined this from multiple annotators in order to get our labels. And in addition to include more diversity, like you also find it on Twitter, we also additionally add distractor images into the dataset to not just have flood images basically in it. And for the second task, we just create a segmentation mask of the flooded areas by ourselves. We had in total 15 teams participating here, and 11 of them submitted their runs. In total, if you look at the number of submissions, it was quite high with 63 submissions, and most of them focused on the first task, while only half of them participated on the last segmentation task. So there are quite some challenges about the processing of this new kind of data. And here I want to show you some of the approaches which participants did. For the first task, it's first of all to notice that the results, which you will also later hear, are extremely diverse. So there are many different approaches on this problem. Different kind of features which have been used based from deep learning, but also basic features from information retrieval. Same holds for metadata information, for textual information, word embeddings, but also different kind of metadata. For example, text and titles are sometimes misleading or too lengthy because sometimes they are copied from Wikipedia, for example. So they confuse basically this retrieval task. And we see here also different classifiers which have been used. Some part is mainly focusing on deep learning, on CNNs, relation networks, also LSTMs for the language part, and also from the traditional machine learning, random forest, SVMs, and logistic regression. Since we also considered here multimodality of combining text and visual content, we have also different approaches for the fusion, late fusion and fusion at the feature level, which have been discussed, and also something very important of combining this dataset with more additional resources. So the task itself was quite open, especially for the last 2 runs, and people used YFCC data, Google images, DBpedia, Spotlight, for example, to augment the images and improve the algorithms for it. Yeah. So for the second task, also it's quite diverse. However, some trend which you can see here is that most of the approaches are based on neural networks. So one paper was, for example, using generative adversarial learning. Others used segmentation networks and adapted this to satellite imagery to cope with the additional bands which you have in these satellite informations. And others also used a patch-based approach, where they extracted features and trained then some support vector machine on top of it. And we also had one team which focused very strongly on remote sensing, so they computed, for example, Borth indices and vegetation indices, and used this in an unsupervised and supervised manner, and achieved also quite good results. So that's an interesting area also, to not just go always with deep learning, but also with domain knowledge in this context. Here are the results for the first task, and something that you can see is that the submissions itself are quite diverse. So visual content is sometimes quite high, but then metadata itself is not that good. However, what turns out is that metadata in combination with visual data improves in almost all of the cases. Here I have the average precision at 480, which is our which is the hardware problem basically. And something that you can see here is the best result which we got, it was around 95%. So it was extremely high on this task. However, you see that not all of them are that good, so it really depends on the approach which you're using. And we will learn later on more about this. So far, Multi-Brazil, I would announce right now, was winning this challenge. So they did really a great job. And you will also later hear more details about this. And just to not wonder, this one is our submission, but it doesn't count in this ranking basically. For the flood detection, we have here also for the different, so we have 5 runs, and we evaluated this on 2 datasets. One dataset using the same locations which have been used in the development set, but different patches which have not been seen. And you see also that the best result was around 80, 86, so quite good already. And for the new locations, it was the second dataset, which was more about in order to see how well the solutions generalize also to new data, to new locations which have been not covered in the development set. And you also see that some of the approaches are quite similar, a bit lower, but still it's at around 80%. So detecting these flooded regions are possible and actually working quite good. And now I want to come to the conclusion of this task. So what you will see is that there are many different approaches for both tasks, which have been here addressed. One major outcome is that multimodal fusion is very important. So just looking at textual information is often not enough, especially quite often very misleading, and same holds for images itself. So the fusion of both is very important. Another outcome is that scene-end features are quite often used, especially for the visual task. And what also turned out, which you will see later, is that it really depends on the data set the models have been trained on. So a classical image network is not always the best, especially for the retrieval task here. And since we also have this quite high accuracy already on the retrieval task, we are now thinking of how can we also go one step further to quantify basically the impact of the event. So is it just a flooded field, or is it really a destroyed building with a very high impact, and to quantify the extent of the disaster basically. Something that we also could see is that on the satellite information it was already quite good, the accuracy, and then it would make also would be very interesting to also incorporate more temporal dimension into account, to track this over time and then use it also in a predictive manner, for example by combining it with topological maps in order to predict from the past, similar like also Tom already said, in order to predict how floodings might occur, at which position they might occur next. That's it for my presentation. And
thank you very much.